What's 1/2 of 2 pi?
Pi.
Minus 0, minus 0, minus 0. So what's the final answer? Negative 32 pi. And again, you go, and that's the flux of the curl of F. Let me go with that. Super job. Hey, one last problem. Let's do another one of these. You got it. Hey, sometimes it can happen on the test where a student looks at the problem, they didn't see the part U Stokes theorem, so they start trying to attack it this way. Now, sometimes it's not a big deal. They can get the answer, but it depends on the vector field. If the vector field's nasty, this can start getting really crazy. I've seen it happen before. And the student just keeps going with it, like, I'm going to try to solve this. And then their integral gets crazy. So if that happens, just realize, go, oh yeah, they said U Stokes. It should be easier doing this as a line. All right. Hey, we're going to attack the next problem the same way by the directions. Oh, I want to make sure. Is you still copying?
Yeah.
I'll wait.
No, I got it all.
Oh, you did? Oh, you did? That was good? Cool. Good job. All right, last one. Last problem. Use Stokes to evaluate this. What's the vector field? So now I'll do 9. 3z minus 3y, comma, 3x plus 3z, comma, 3z. What's S? S is the hemisphere. Below the xy plane. They give the hemisphere equation, everyone? X squared plus y squared plus z squared equal to 4. They make a note, comma, z is less than or equal to 0. That's indicating it's below z equals 0. That's why they wrote that. Below the xy plane. And they mentioned it has downward orientation. All right. Downward orientation. Well, this is how we're going to attack it. We'll see there. So again, with Stokes' theorem, we should always make a picture, right? Make a sketch, make a picture, so we can look at the surface, we can find the boundary curve. That's the one section. Every problem we do, we want to see where is that curve, so we can parameterize it. Or if we're doing the other side, where's the surface, so we can parameterize the surface. But right now, do you agree it's all about the curve? Let's draw this thing. And we'll talk about that downward orientation. This is the first problem today where we had downward orientation. That won't be difficult to deal with. So now, and when there's a hemisphere below the xy plane, okay, I'll just go like this. There's the curve sitting in the xy plane, and here's the bottom hemisphere. Right there. Make it look like a bowl. Now, this yellow curve is in the xy plane, right? That yellow curve is in the xy plane. It's in the plane x, z equals 0. But that's our boundary curve. Does everyone see the boundary curve?
Mm-hmm.
Nice. The bowl's underneath it, though. So if it's downward orientation, which way the normal vector's going?
Clockwise, right?
Yeah, and so he says clockwise. That's the key to this problem. when we work this line integral right now, let's remind ourselves we're going to have to go clockwise as viewed from above. So before I did cosine before sine. To make it go clockwise, what can you do? Just put sine before cosine in terms of the x and y components. That'll do it. That will simply do it. So when it comes to counterclockwise orientation, I would do cosine for the x component, sine for the y component, for counterclockwise orientation. You're all telling me, hey, we're going to have clockwise orientation on this thing, as viewed from above. So if you go, what do you mean by clockwise? I mean like if I viewed looking at it downward. So to have clockwise, when we set up and we parameterize that curve, let's put sine on the x component and cosine on the y component. Or if you want, if you don't like that idea, just keep it cosine sine every time, and in the end, on this problem, just put a negative up front. It'd be the same thing, okay? It'd be the same thing, but I'm gonna put a sine before the cosine. All right, so the big deal over it is all about that curve. That curve C. It's the curve in the xy plane. Can you help me parameterize that? What's R of T? It's that circle right there. Who cares about the bowl? I don't care about that hemisphere. It's all about the boundary curve. Anybody know the radius?
2.
Man, you're good. Look how you did that in your head. Because z would equal what? 0. So you now have x squared plus y squared equal to 4, the equation of that circle right there. So I'm going to write it right next to it. The equation that circles x squared plus y squared equals 4 in the xy plane. That's that circle. So to parameterize that circle, I'm going to do 2 sine t, 2 cosine t. Notice I'm putting sine before cosine because of
Clockwise.
clockwise orientation. Anybody know this number?
4.
No. And don't worry, I want you to see why, Harry. Because last time, that thing was way up at z equal to 4. That curve, and it could be my sketch, but that curve, right, it's sitting in the xy plane. And in the xy plane, z is just equal to what? 0. So I'm going to make that a 0. But you got it. Hey, what if this was, well, let's not say it was a sphere, but let's say it was another parabola that went all the way up to like z equals 9, and the boundary curve was sitting way up at z equal to 9. Then I would have made that a 9. But if it's sitting in the xy plane, everyone, that curve is sitting in the xy plane. I know it looks distorted on the board though, so it could be my drawing here, Rich. I'll just go over there and be like, this is hitting at 2. And this is hitting over at -2. And that's hitting at 2. Extend that 2. That's hitting at -2. Just make a decent circle. Alright, what's our prime at T? Our prime at T is 2 cos T, -2 sine T. What's the derivative of 0?
0.
Good. What makes it go one full loop? 0, 2 pi. Alright, F composed of R of T dot R prime of T, right? We got the clockwise orientation. Clockwise. As viewed from above. Clockwise as viewed from above. Why? Because they said head downward orientation here for normal vectors. So when I am actually going to draw that direction on this curve, counterclockwise would go this way. This is the direction it's moving. That way. Or that way. That's the path it's taking. Some part of it. It's going that way. Going that way clockwise. Alright, here I go. 0 to 2 pi. And here's F. Can you help me stick in the Z's and Y's? 3 times 0 minus 3 times 2 cos t, comma, 3 times 2 sine t, plus 3 times 0, and then I got just 3 times a 1. I love those zeros. Dot R prime of t, which is 2 cos t, negative 2 sine t, 0 dt. Dot, get the answer. What's that dot product though? That's 0 minus 6 cos t times a 2 cos t is? Good job. Negative 12, oh, and thank you, he says cosine squared. So in that 2 times 0, you don't have to write that. But this times this is negative 12 cosine squared t. Plus, what's all this times that? Negative 12 sine squared t. And what's the z component? Oh yeah, 0 times 0 is what? 0 times a 0 is 0. Any suggestions on how to do that math problem?
Negative 12 times 1.
Oh, yes. When we don't have to do that power reduced identity. Fact out the negative 12. 0 to 2 pi. What's cosine squared t plus sine squared t? I love it.
1.
I didn't know this was going to happen until the end. This is just a what? Because I mean, seriously, when I put these practice problems together, I'm really taking problems, actually, good problems from the textbook. This becomes negative 12, 0 to 2 pi dt. Hey, be careful. The worst part is we did all this great work and I mess up the end. Single integral 1 is not area, is it? The integral from 0 to 2 pi, and there's a 1 there, right? Is negative 12 times just, this is just going to be 2 pi, right? Negative 12 times 2 pi. Final answer?
Negative 24 pi.
Boy, we had a lot of negative answers to that. How did this just happen that way? So you could say that's the work done by a particle that moved around that path all the way around, or you could say you just found the flux of the curl of the vector field. 2 ways to look at that. Cool. Erase all of that. Let me hide all this off right here. Separate. Anybody have any questions on this stuff? Is he still copying? Well, I'll have to erase the last problem, everyone. Super job. Yeah, that's it. So, hey, rest of class, you can take off if you have questions for me. Super. Monday, test 5. Practice set 5 due. Tuesday, just review. Sound good?